Let's draw a snapshot graph for a sinusoidal wave. The snapshot graph is one where we plot displacement versus position, and we're going to draw a pure sine wave, meaning it comes out of the origin and oscillates like that. Okay. This, let's go ahead and pick a time. All snapshot graphs need to have a time, so we're going to say this is at t equals 0. And the other bit of information I need to know is what direction is this wave traveling. So I'll just say it's traveling to the right with speed v. Okay. So my goal is to try and describe that mathematically. Okay, so it is a function of position, and though the wave is also a function of time, here I'm showing just one time, t equals 0. So I can write that d, which is a function of all positions, but one time, okay, t equals 0, is equal to, and I've got to figure this out, it's definitely a sine curve, so it's going to be a sine of something. But before I do that, sine goes between -1 and 1, and this is going to go from its amplitude to its negative amplitude. So I'm going to put an amplitude out front, so that way the amplitude times sine will give me everything from the positive amplitude down to the negative amplitude. Now the question is, what goes inside the sine? Okay, we know that sine needs to act on an angular measurement, a radian or a degree. Okay, we're going to focus on radians. Okay, so we need to think about, what is this doing? How do we plug this in? We know that at 0 it's going to be 0, and at this point right here, this wavelength x equals lambda, so we can note that from here to here is one wavelength. That's our wavelength. We're repeating the cycle. When x equals lambda, we are repeating the cycle, which for an angular measurement, that's 2 pi. 2 pi radians gets us around the circle. So I could write 2 pi here, and then I could put in that ratio. So if x equals lambda, I'm at 2 pi. If x equals half lambda, I need to be at pi, and the way I can do that is put x over lambda, and I can get that for every piece now. So if x is 0, this is 0, sine of 0 is 0. If x is lambda, x over lambda is 1, I get 2 pi, sine of 2 pi is 0. If x is pi, or if x is half lambda, so right here I've gone half the way, I get 1/2 times 2 pi, which is just pi, and sine of pi is again 0. And I could keep going. If this is a quarter lambda, I'd get pi halves, which is a maximum of 1, so on and so forth. So doing our radian, 2 pi radians, times the fraction of a wavelength we've traveled gives us the proper angular measurement for us to predict where is this as a function of position. Okay, that's great. That is a great description of this wave. But my goal now is I want to find out how to describe it for all times, not just t equals 0. So to see how to do that, let's consider this having traveled it's traveled a little bit, so time is now a little bit bigger than 0. And so let me just draw it again. And this piece of the wave has traveled a short distance. This piece of the wave has traveled a short distance. So we can get that looking good. And then we can just keep doing that, and we'd end up with something like that. Okay, and apologize, I should have drawn that down a little bit more. But each piece of the wave is just shifted over. It's just shifted over a little bit. And now here, let's say this is some x I'm looking at, some x value I'm looking at. And I might say, okay, how do I describe my full function? How do I describe this whole wave now? It's not a simple sine curve anymore. It's not coming out of the origin here. It's starting some way different. This is later time too. This is greater than 0. So I need to figure out how to describe that one. Well, the clue is to recognize, well, this looks like that one when it was back here. So if I took that one and shift it, then I get this one, and that's in fact what it's doing. The wave is shifting over. So I want to see, how can I relate this one in terms of the x values here to this one at t equals 0. And if I think about it, this wave moved a certain distance. In fact, that distance, if I were to mark that down here, this distance it traveled was v times t, whatever this time was. It traveled that far. So this wave looks like this wave at t equals 0 for positions vt less than where I really am. Okay, so this looks like that one. So mathematically, I can write d at x and non-zero t. It looks like d at x minus vt and 0t. Okay, so the true function for this time and all positions measured here looks like this. Looks like the position earlier, an earlier position, and at 0t. So I've just traveled that distance. So when I write that out now, I just plug this in for x up there, and so this now equals a sine of 2 pi times, now x is x minus vt, divided by lambda. Close the sine parentheses. Okay, so let me expand out that sine. A sine, I get 2 pi x over lambda for this first one, minus, and I get a 2 pi vt over lambda. Okay, now I'm going to do a couple jumps, and you'll have to follow it, and you can look back at previous material. But if I remember that v over lambda is the same thing as frequency, remember velocity equals lambda times frequency, so that means the velocity over the wavelength equals frequency. And so this ends up just being 2 pi f times t. Alright? And one even simpler way of writing that we often do is we can write that as omega, the angular frequency. Because we're just taking 2 pi radians times the regular frequency gives us an angular frequency, this omega here. Now this equation is describing this wave at any time and any position. But we got it by referencing the wave at t equals 0, what it looked like, and then just translated it by how fast it's moving and how long we're looking later on. So this is now our equation that describes the full dynamics of a moving wave, a traveling wave.